Good morning, I'm Tabitha Thompson with NASA's Office of Communication. Welcome to What's on Board at NASA's Kennedy Space Center. Over the next hour, we'll discuss research investigations launching on the upcoming SpaceX resupply mission to the International Space Station. In addition to crew supplies, the spacecraft will deliver new experiments that have the potential to improve life on Earth. In addition to taking questions from people attending in person for the launch, you can submit questions via social media with hashtag AskNASA. Joining us first are Tara Rutley, Associate Program Scientist for the International Space Station, and Patrick O'Neill with the Center for the Advancement of Science in Space, which manages the U.S. National Lab on the space station. Tara and Patrick.
Thank you. Let's see. Good morning. It's very cool to be here. I want to just open by saying Patrick and I are excited to have a little coffee chat with you guys this morning about the science that's going up on the International Space Station. I don't know about you. It's been a long time since I've been here at KSC, and when I drove up this morning, there's nothing like the sight of everything that's happening out there. It's very alive. It's very exciting to be here. I think the audience here is really ramped up, and we're all just excited to see what's happening here tomorrow. But I'm really excited about the science that's happening on the space station. That's where I'm from, and that's why we have the space station, is to do research and develop technology. Patrick's going to tell you a lot about why we do it for benefits on Earth. We also do it for exploration. And this particular SpaceX launch is going to send supplies and research up that's going to support over, well, just about 300 investigations that's going to be happening over the next 6-month period. They're going to represent, those investigations are going to represent 800 scientists' work on the ground around the planet. That's going to be done by 6 people on orbit. So the science is being multiplied. The technology, the advancements in how we do business and how we understand how things behave is going to be advanced over the next several months because of this particular flight. And we get to get samples home because of the SpaceX return vehicle as well. So why do we do science in space? Most of you probably have some kind of a clue. If you're here, you know why. For those of you who are just kind of, asking yourselves, I don't really know, because it's cool, because things behave differently. Yeah, it's a resource that only we have access to, that you can't get access to here on Earth. The spaceflight environment, not just microgravity, and take that gravity vector out of the work that you do, but also the external environment of space, the ability to look down at our planet, the ability to look beyond our planet, the ability to test new materials in the external environment, the ability to test inside the environment by using microgravity to see how changes happen in living systems, or how unpredictably physical sciences problems can behave. Things that you know that are predictable in terms of science or everyday behavior here on the planet could be totally unpredictable once you get into space. And that's why the scientists want to use that environment, that particular laboratory that you can't do here on Earth. And it's a good time to be a space scientist or a space technologist or just a very curious human being here on Earth. With that, I'm going to pass it along to Patrick, who can tell you a lot about some of the investigations that are going to be happening on the National Laboratory portfolio.
Cool. Well, thank you very much, Tara, and thank you all for being here this morning. Again, my name is Patrick O'Neill. I'm with the Center for the Advancement of Science in Space, and we do manage the U.S. National Lab on the space station. Show of hands real quick, because one of the cool things about the NASA social group that typically comes out for this is that it kind of changes a little bit. How many people here knew that the ISS was a national laboratory before showing up this week? Oh, well, that's good. Oftentimes, there's a lot of people that really don't know that the ISS was declared a national laboratory. And a little background on that: in 2005, Congress they wanted to try to open up channels for researchers. And the reason they wanted to do that was because they looked at the research that NASA was doing, and they were saying, "Gosh, you know what? There's so much incredible things that are happening on the space station, and it's such an enabler for everything from life sciences to material sciences, physical sciences, technology development, Earth observation, remote sensing, student research." But right now, all the things that NASA's doing, it's kind of focused more towards exploration. What if we turned things around and started looking at how we can use microgravity to benefit life on Earth? That would enable so many more researchers to take advantage of this platform. And so that's what the National Laboratory is about. It's about providing this microgravity environment to you. This is something that we have all invested into, and something that now is available for researchers to take advantage of. So Tara talked about the excitement of being here, and I think that it's a very exciting time in general to be involved in kind of the launch business. And more importantly, though, from us, though, it's exciting not about just the launches, but what's going to be happening inside of those launches, what's going up to the space station. That's what we're here about to talk about the science. And, again, as we kind of morph into the National Lab payloads, there's an awful lot that's going up. And so one of the things that Tara alluded to was the notion that SpaceX has the ability to not only send research to the space station, but to also send research back down to the ground. And so what we've come to find with a lot of the SpaceX missions is that it really caters heavily towards the life sciences. And on this particular mission, that is no different. So in total, we have about over 35 ISS National Lab payloads that are destined for the space station, the vast majority of which are focused on life sciences. And it really does kind of stretch the boundaries of life science, from protein crystallography to stem cell investigations to cell culture design, drug discovery, drug development. And all of these are done with the intention of benefiting life on Earth. So we're going to hear about some of the researchers today and some of their investigations. And in general, again, it's just a really great time to be involved in space-based research. And I guess at this point, we're happy to answer any questions that you might have about some of the payloads that are on this manifest.
If you have a question, just raise your hand and someone will come to you with a microphone.
So those who are on the International Space Station right now, they're going to get the payload from the CRS-10 that's going up. What kind of scientists are there now, and what kind of experiments are they going to perform?
That's a very good question. So the astronauts who are going to receive this set of payloads are going to perform experiments across many different disciplines. We have experiments to look at the Earth. We're sending up an aerosol experiment. You'll hear more about that this morning, looking at ozone. They're going to be performing a whole bunch of human physiology experiments. So we've got resources that are going up to support that, because we want to advance benefits to knowledge about that on Earth, but also huge for space exploration beyond the Earth orbit. Biological sciences, you'll hear about some of the genetics and some of the bacterial research that's happening this morning from some of our speakers. We've got physical sciences, we've got processing of materials, alloys, we've got some fluid physics, we've got a whole suite of things. And we've got educational experiments going up too that students themselves designed, as well as little CubeSats that get launched from the space station from commercial companies. So this particular crew is going to receive a wide range of things, and they've been trained on everything they're supposed to be working on, and they are knowledgeable in it, and they are going to be our proxy scientists for this mission.
This Ask NASA question is from a student named Janet, and she asks, will these supply missions help achieve the goal of transporting humans to Mars?
Oh, definitely. That's a really good question. Always. So exploring beyond low Earth orbit, that is one of NASA's main goals, right? So that is a good question, because this is the time now that we have this laboratory in microgravity to test out every type of technology and understand every type of change that happens in the body, so that we can go and explore Mars. So quite definitely, a lot of the human physiological sciences will take charge of that, but also some of the technology development too. So you'll hear about some of those this morning that are going to enable that as well, from places and groups such as the Space Test Program that the DoD is sponsoring this morning.
So speaking of physiological changes, I know that we learned some really interesting stuff when Scott Kelly came back recently, particularly about the telomere lengthening. And I know everyone's super excited about that. I'm very excited about it. Yeah. And I know they've got a PCR machine up there on the space station. So is there a plan to follow up specifically with that?
There are plans. The Human Research Program is still looking at the results of that investigation. I too, when I heard the telomere lengthening, I thought, I don't even know how that's possible, right? So spaceflight, go figure. But so those results are still being investigated, and we're going to give some time for the Human Research Program to come up with a new plan and how they want to go forward on those evaluations. But the technology that we are creating for space stations, such as the PCR device or all these other genomics analytics that are now on space station that all scientists have access to, are part of the suite of improvements that can take us to the next level in those kind of studies.
I think we could take 2 more questions, so if we could.
Okay. Because of the number and diversity of experiments, what kind of education and prep is required of the people who are on the space station? Like, what is the length of time that they have to prepare for these experiments?
So, and feel free to jump in anytime. You know,
I'm
He's
just the
gonna- he's
marketing
gonna-
guy.
I'm just-
You're the science.
I'm just going to do
person
all
here.
the talking. Patrick's like, you got this. So the crew members train about 1.5 years once they're assigned to a space station mission, and they have to learn about the vehicle, right? They've got to learn how to stay alive, how to stay safe, how to keep the mission going. But also part of their training, very critical part of their training, is the all the science. So they're assigned to a set of science experiments, and that becomes theirs. And so they're trained on those particularly all across the country. They'll work with the investigators. They'll work with the trainers at Johnson Space Center and at Marshall Space Flight Center. And they ask questions, and then once on orbit, they can call down and talk to the investigator too if they need to. So it's a very exciting time. Not everything that happens on space station in terms of experiments are using humans. Some of these investigations are automated, which is very cool too. But they're trained all through the science, and they are also trained before they're assigned. They have baseline training that keeps them up on their life sciences skills and their biomedical skills and their physical sciences and those kind of things.
Okay, so mine's not as scientific, but it has to do with taking stuff up there. A couple weeks ago, we had the Super Bowl, and I noticed that the people had the right jerseys. And I'm thinking, do they just have a jersey for every team that could possibly win the Super Bowl? I mean, how do they get that up there?
Probably so. I heard I was on one of those Super Bowl tours with a public affairs person, and they were asked the same question, and she said, lots of preparation. I don't really know, but my guess is somebody's pretty smart on what's happening on the football field there, and they're watching. Maybe they're in fantasy football. No, I don't know, but yeah, someone's pretty smart and can launch these things ahead of time, and it takes a lot of prep. My bigger question was, did they send that football up inflated or was it deflated? You know, because you think of all the pressure changes, but you know.
Thank you both very much.
All right, thanks, guys.
Thank you, Patrick and Tara. The great explanation of the research headed up, as well as what the crew does to prepare. Next, we'll hear about 2 instruments that will provide valuable Earth science data. Joining us are Michael Freilich, Earth Science Division at NASA headquarters, Mike Cizeski from NASA's Langley Research Center, and Richard Blakesley from NASA's Marshall Space Flight Center. Gentlemen?
Well, thanks very much, and thanks to all of you for waking up early in the day and coming out and helping to spread the word to all of your followers about the great things that we're doing on the ISS and in the CRS-10 flight. So when CRS-10 launches, as you heard, it's actually going to have 2 Earth-observing instruments on it. SAGE-3, to measure atmospheric constituents and aerosols, and a lightning imaging sensor. So we're going to go from the Earth to the space station in order to look back down on the Earth. And that's not as weird as it might seem, because our planet is a really complex system. We have processes on the ocean, on the land, in the atmosphere, physical processes, chemical processes, biological processes. And the key to understanding our planet is to not only understand individual processes, but the connections between them. And only from the vantage point of space can we make measurements that have global extent, but high spatial resolution, fine resolution on the surface, frequently at every point, over long periods of time. First slide, please. And in NASA, what we are doing in order to understand the interactions between processes, our whole environment, is that we are making measurements of many different variables using an on-orbit fleet of about 20 spacecraft and major instruments in the lower half of this visual. And we have firm plans over the next 5 years or so to launch about another 20 instruments and major missions into space so that we have measurements of many different variables all at the same time covering the entire globe. Next, please. And we are not only flying our own satellites or putting instruments on partner satellites or even private sector satellites, but of course, since you're here today and we're here today, we are also making measurements from the International Space Station. And it turns out to be extremely efficient and, from a scientific standpoint, extremely useful to use the space station because the space station orbit is really unique. And we presently today have one instrument, the Cloud Aerosol Transport System, which is operating on the space station. LIS and SAGE-3 will be launching on CRS-10, and we have firm plans for about another 5 or more instruments to fly to the space station over the next several years. So with that, I think I'll stop with the introduction and turn to my two colleagues here, Mike and Rich, to talk in detail about the measurements from SAGE-3 and the Lightning Imaging Sensor.
Thank you, Mike. I'm very excited to be here today to share with you about SAGE-3. And so if we could get the first chart. I'm going to start off with a little bit of history so you guys have the right context and can go ahead and understand what we do and how we fit. The first SAGE-like measurements from space were made in 1975 by astronaut Deke Slayton. Deke used a little window-mounted sun photometer to go ahead and measure the atmosphere during sunset and sunrise as the Apollo capsule rotated or orbited the Earth. Since that time, scientists and engineers at NASA's Langley Research Center, where I'm from, have basically continually improved that technique. And next chart. The SAGE-3 instrument payload you see behind me is the latest in that series. We're going to be mounted outside of the space station, okay, in the vacuum of space. And from there, we'll go ahead and make high vertical resolution measurements of the atmosphere, of ozone, nitrogen dioxide, water vapor, and aerosols to go ahead and understand our atmosphere in the ozone layer. Back in the 1980s, scientists warned the public about the dangers of chlorofluorocarbons, okay, mostly freons used in air conditioning. And the U.S. and the world took action. Right? They implemented the Montreal Protocol to go ahead and eliminate the harmful chemicals to protect the ozone layer. And the great news, guys, is that it worked. So data from SAGE-2 and other NASA sensors that Mike just went ahead and showed you have showed that the decline of the ozone layer has stopped, and atmospheric models are predicting a full recovery by mid-century. So how does SAGE-3 fit into that? We're going to make measurements right now from the space station that show the recovery is on track. So I think that from a science perspective, it doesn't get any better than that. Behind me, next please, I've got a short video. This is an animation prepared by the robotics team at the NASA Johnson Space Flight Center. And this is showing the assembly sequence on orbit, okay, that's done all by robotics to go ahead and install us to the space station. And what you're seeing here is really accelerated. This is 13 days of work, 2 shifts, in about 30 seconds. And just kind of think of this. This assembly sequence is extremely complicated, not quite as complicated as the Earth system that we're going to go ahead and help measure with SAGE-3. To wrap it up, we're extremely excited about launch on SpaceX, okay, getting on with the installation sequence, and you guys understand how important the data it is that we're going to collect from the space station to monitor the health of the ozone layer. So if you guys are interested in more, check our website out, sage.nasa.gov. Thank you.
Good morning. My name is Richard Blakesley. I'm the science lead for the lightning imaging sensor. This was an instrument that was developed by NASA Marshall Space Flight Center and the University of Alabama in Huntsville. And we're really excited for this mission of opportunity to place the LIS instrument on the International Space Station to measure global lightning. But let me begin by noting that this instrument really is a tried and true sensor. And the reason I say that is it's a carbon copy of an instrument that flew on the tropical rainfall measuring mission for 17 years. Therefore, by placing the LIS instrument on the International Space Station, we can not only continue that 17-year record of tropical lightning measurements, but we can also expand the latitudinal coverage to latitudes that were not possible to see from the TRIM spacecraft. In addition, we're excited that this instrument and the measurements from this instrument can be used to help calibrate and validate the new geostationary lightning mapper. This was an instrument that was launched in November on NOAA's newest weather satellite, the GOES-16. But however, one of the most important science objectives for this mission is to better understand the processes that create lightning and also the connections between lightning and subsequent severe weather events. And NASA recently just experienced one of these in one of its facilities when they had a damaging tornado. So our improved understanding will lead to improved weather forecasts, and this will lead to saving lives and property here in the United States and also elsewhere in the world. Could I have my first video, please? So once the LIS is delivered to the International Space Station, like SAGE, it will be robotically transferred to a position on the outside of the space station where it can continuously observe the lightning as the space station orbits the Earth. What LIS actually measures is the amount, rate, and radiant energy of lightning. And it does this both during the night and day, and it does it with high detection efficiency. And what that means is that about 90% or more of the lightning that's within the LIS field of view is detected by this instrument. One of the very unique features of this instrument, however, is that it's able to detect the lightning during the daytime. Conventional cameras cannot see lightning during the day. And it does this by using a narrowband, near IR channel and special processing to extract the weak lightning signal from the very strong solar light that's reflected off of the clouds. Could I have the next video, please? So this video shows what lightning looks like from space, taken from the International Space Station. And what you can see is that the space station provides an excellent vantage point for viewing lightning. And the Earth produces a lot of lightning. At any instant in time, there's from 1 to 2,000 thunderstorms occurring, producing 45 flashes per second on average. And even that number was determined from our previous mission, the LIS on the tropical rainfall measurement mission. So our team and really a host of scientists worldwide are excitedly waiting for this instrument to be turned on and for the data to start flowing so they can apply these measurements to studies in weather, climate, atmospheric chemistry, and physics. So thank you.
With that, we'll open it up for questions. Again, if you have a question in the room, raise your hand. If you're following along on social media, make sure you ask your questions via #AskNASA.
What are some of the practical non-weather science applications for studying the lightning patterns?
So some of the what might be considered a non-weather science would be looking at the relationship between lightning and the nitrous oxides. Lightning is a natural producer of nitrous oxides. It's one of the largest producers. And that nitrous oxides can also then produce ozone, and so we want to know what's actually happening that man isn't producing. So this is a useful way of doing that.
I was really interested to hear about the potential ozone recovery. I wasn't aware of that. That's amazing and really exciting. And in light of that, I was actually going to ask this question anyway, but it's even more pertinent now. We obviously have an administration that's actively pursuing deregulation of waste and emissions, trying to roll back other environmental protection and climate change policy. Can something like SAGE 3 and the data that you're gathering help to present more concrete evidence that what we're doing is or is not hurting the planet and help to influence that future legislation?
So our job is really to go ahead and produce the data. And so the SAGE has been doing that, going back to the 70s. The SAGE 2, we flew on the Earth Radiation Budget Satellite, launched in 1984, lasted 21 years. And so we've been producing high quality data that we go ahead and openly publish and goes out to the scientific community so they can address exactly that kind of question. And my expectation is that we'll do that continuing into the future.
We have a question toward the back.
Oh, Heinz, could you just explain a little bit of the difference between the lightning sensor on this and then the recently launched satellite? Is it just the altitude that gives you a different perspective?
Yes, so the geostationary lightning mapper is actually, its heritage is based on this instrument that we're flying now. Of course, because it's geostationary, it's going to be looking at the lightning in the western hemisphere. It's going to be looking at it continuously. This instrument will be observing lightning globally, but it's also a well-characterized sensor, and so it's very useful. We want to continue our climatic record of storms, and by intercomparing the two instruments, we'll be able to do that.
We have a question here.
Good morning. Excuse me. I'm Emily Bonedrake. I'm a social studies teacher at Morris Tech in New Jersey, and my students have been learning how this mission connects to things in history we've learned about from the scientific revolution and exploration and stuff, but also how it can affect humanity now. So the question that was asked the most by my students is that we studied the idea of a Renaissance man or woman or a polymath, and right away the talk of lightning as a history teacher makes you think of Ben Franklin. So they've been curious as to how modern Renaissance men or women are impacting these scientific missions today. So they were just curious, like on a personal basis, has there been an interest in the humanities, something outside math or science? We've already mentioned political aspects and historical aspects that have inspired your curiosity and made you better scientists or researchers or things like that.
That's really a great question and a great insight from your students. As we said, the Earth is really complex, but it's the place that we all live. We all have experiences and some limited understanding of the planet. In order to understand more, we have to be broader. We have to not just measure the atmosphere, not just measure the ocean, not just do research on land, but we have to understand how the processes interact. That requires a broader scientific understanding, but since it's the planet on which we all live, we can take that understanding very straightforwardly and turn it into societal benefit. The predictions that are being made, the policies that are based on the analyses that we do require a tremendous knowledge of social sciences, of national objectives, etc. beyond just working in a laboratory or doing focused research. So Earth system science is a key broadening feature of what it is that we do, and makes what we do with its societal benefit connections probably unique among all of the scientific enterprise.
Thank you. Thank you, gentlemen. Thank you for the great questions. Up next, we have Jolynn Russell to discuss Raven, a technology demonstration aimed at improving autonomous docking. Ms. Russell is the Deputy Robotics Program Manager of Goddard Space Flight Center's Satellite Servicing Projects Division. Thank you.
Thanks for the introduction. It's great to be here with all of you. As everyone else has shown their enthusiasm, we too are excited to take Raven to space station. I'm really honored to be here to represent a great team that brought this project from basically conception to ready to ship within 18 months. So that's no small feat in of itself. Raven is a technology demonstration mission that will be testing and advancing an autopilot system for spacecraft. It has 3 sensors that, coupled with some advanced algorithms, will be used to track the incoming and departing visiting vehicles from space station. So this is a brand new technology for NASA. We're really excited about it. We'll use this for many applications, the first of which is a Restore-L mission, which is a mission that is focused on refueling, where we'll be building a satellite that will rendezvous, capture another satellite, and we'll refuel it at that point, extending the capabilities of satellites in space. In addition to that, we can use this technology for Journey to Mars. You can imagine that there's going to be refueling and all kinds of other rendezvous things that we need in that as we move on to that new frontier. To put this in a little more perspective, we have a life-size Raven here to show you what we're sending to space station. The silver box is the Raven sensor enclosure. In that we have a LiDAR, so this is the send and receive apertures. We also have an infrared camera and a visible camera. So these 3 sensors together provide data about the vehicle as it's approaching. We have a 2-axis gimbal over here, so this gimbal will move the sensor. It can rotate it this way, both azimuth and also in elevation. So as the inputs come in, it tracks the vehicle and autonomously, with no input from anyone, decides how to track it until it's birthed. So this is a great testbed for a Restore-L mission. You can imagine that we can prove out one of the most complicated parts of that mission. We also would like to show you a little bit about how Raven came together. So we have a video for that. We built this at Goddard Space Flight Center up in Maryland. We did the work in the clean room. This was a big day for us when we brought together the sensor enclosure here with the gimbal. Kind of bringing the 2 systems together was a big step forward in our process. All the work done here is in a clean room. You can imagine that we don't want to get a camera in space just to have a smudge or a piece of dirt on it. So once we get through the integration process, we depart the clean room. We go into a test suite where we'll go through a vibration test to make sure we can survive the rocket launch. We'll also do some thermal vac testing to make sure we have all the capabilities at both hot and cold. Once we get through all that, we test and make sure we still have functionality. So that's once we get through all that, we're confident that we're ready to launch. Of course, the biggest test of all is the actual rocket ride tomorrow. This is showing once we get there, we get docked on space station. You saw some of the acrobatics that go along with that. We'll go through a similar robotic install for Raven. And this is an image of how we will track the visiting vehicles coming in, switching between the sensors and using that input to track it to birth. Looking forward to this. We should be up there in the next couple days, and if all goes to plan, we will, first thing we see leave is the Dragon capsule that we came in on, so stay tuned.
If you have questions, please remember to raise your hand. You can also ask questions via social media with the hashtag AskNASA. We have a question back here.
Will this decrease the time it takes for like a delivery vehicle to attach to the station? Because I noticed, I've seen one of those before, and you see the vehicle from the space station it looks so close, and then the caption says it'll be connected in like 24 hours, and you go, wait, it's right there. Why doesn't it just connect so fast?
Not trying to speed up that well-tuned process by any means. We're trying to develop the technology for other missions and doing the tracking and incoming, but this will give us some new looks at the vehicles coming in that we don't have before, so we're happy to share those.
Does this kind of sensor require some sort of consistent framework whenever rockets are built in order for it to be compatible, or is it more about the material that's used in order for the sensors to be able to track the location?
So you've hit on one of the very key elements of our whole mission in general. So most of the satellites, in fact, all of the satellites that are in space right now that we would target for refueling and other kinds of operation are not cooperative. They weren't planned to be captured, and so this kind of technology is more complicated in that we're trying to pick up on features that just happen to be there and use those to track. So one of our goals of our group in general is to make things more cooperative, to put certain targets on them so that things are easier to find going forward. But with what we have now, we're trying to develop the non-cooperative aspect of that. So.
Great, thank you, Ms. Russell. And now, please welcome Paul Reichert. He's Associate Principal Scientist for Merck Research Labs, who will discuss the potential value of the space station's microgravity environment for improving drug development. Mr. Reichert?
Good morning. I'm from Merck Research Laboratories in Kenilworth, New Jersey. Glad to see there was somebody else from New Jersey here, which was a pleasant surprise. And I'm going to be telling you about my experiment, or Merck's experiment, to grow crystalline suspensions in space. And anybody who's been familiar with most of the experiments people have talked about in microgravity have been to grow large single crystals for structural studies. And when I say large, this means crystals that you can barely see with the naked eye. But the focus of my experiment will be to grow crystalline suspensions. So I'm looking to grow millions of crystalline particles, a uniform size and high quality and high order. These crystals have applications for drug delivery, for formulation, and for purification and storage. So what does this have to do with microgravity? You know, what does microgravity have to offer us? And actually there's three effects that we're trying to take advantage of. Number one is that there's reduced sedimentation. So these particles, as they grow, have mass. And then as they grow in the solution, they tend to sediment, and there's turbulence around those particles. And that turbulence causes the particles not to be as high ordered as they could possibly be, okay? And the second effect is that there's minimal convection currents. And the way I look at this is that if you ever look at a pot boiling and you see that swirling that's in that pot, that's due to, that's a gravity-driven process where there's not a uniform temperature gradient in that solution. Fortunately, in microgravity, what you get is you get a uniform temperature gradient throughout your solution. So if you have a certain temperature where you need to get crystals to grow, you can very exquisitely reach that point, get nucleation and growth. So we have a really exquisite control of the crystallization process. And the other effect that we'd like to take advantage of is that there is reduced molecular diffusion rates. And well, the way I look at that, it's like a bricklayer who's building a wall, and if he's got to do it quick, what it does is the bricks aren't nicely gapped and with cement in between them, and the wall is kind of crooked. If you can slow that process down and bring in bricks one at a time and have a nice order, you're going to have very nice, well-ordered crystals of high purity. So that's our goal that we're trying to do here. The protein that we're flying for this experiment is actually a very important new drug product from Merck. It's called Keytruda, and that's our anti-PD-1 therapy. PD-1 is our programmed death protein. This drug helps your immune system, it orchestrates your immune system to detect, fight, and destroy tumor cells. All right, so let me just quickly show you some of the hardware that we're flying. All right, the first hardware is the protein crystallization growth box, all right? And then this is the 6-pack, so there's 5 of these 6-packs in here, all right? And then there are 6 individual chambers in here. In each one of these chambers, there's a tiny little insert where we put the protein and a little bit of precipitant, and then below that is precipitant that's there. And what happens is on launch, that insert is turned sideways so it's protected, all right? And then once the astronaut gets up there, he just turns the crank and turns that insert in vapor contact with the solution below. And what will happen over time is that drop will shrink, and if we're fortunate and the conditions are right, we'll get crystals to grow, okay? All right, the other hardware that we're flying is called the protein crystallization facility, which is an aluminum box that's under vacuum. And then there's individual 1 ml bottles that are in there. And this is where temperature comes in. We have our monoclonal antibody in there, and we have our precipitant in there, and the aluminum cap with the change in temperature. This is in an incubator. We can get a nice temperature gradient across that bottle, and that's how we hope to get really high quality, pure protein to crystallize. And we have 2 of these modules dedicated to 2 different conditions to get crystals for drug delivery, and one of them are dedicated to where we take relatively very impure protein. We take the protein as it's grown in a fermenter, and we can get it to crystallize on Earth, and we want to see what happens in a microgravity environment. So I'm very excited about this experiment because of how different it is to past protein crystal growth experiments. I'm also like to thank CASIS and NASA to give me an opportunity to do research in the most unique laboratory in the world. And it is a laboratory for doing research. I would like to say that we plan to publish these results so that we can share this with the broader community. And I'd like to say that we hope that these experiments benefit both our patients as well as caregivers. So that's all I have.
Thank you, Mr. Reichert. Again, if you have questions, just raise your hand, wait for the microphone to get to you before you start speaking so that everyone can hear. And if you have a question and you're following along via social media, you can submit your questions via the hashtag AskNASA. We have 2 questions in the back or in the middle.
Hi, thank you for the demonstration. It was very cool. So in addition to the programmed cell death investigation, what other pharmaceutical applications are you looking at with this particular experiment?
Well, the three things are drug delivery, and one of the issues with monoclonal antibody therapy right now is that there's relatively insoluble drugs. So they generally have to be given in an IV setting as a constant infusion. And we're looking at opportunities to make a concentrated crystalline suspension that could potentially be given as a sub-Q injection. So this could alleviate those hours that a patient as well as a caregiver has to do 3 times a week. And then get a single injection in a doctor's office or self-injection. So that's one of the key, applications that I could see that could come out of this.
So if this experiment is successful in space with the crystallization, how will you then replicate it for the masses?
I always get that question. All right. So there are things that we can do. I mean, what we're going to try to do is to get learn what are the key variables for crystal growth that's there, and then apply them to Earth processes. We don't have plans of doing manufacturing space. I personally would like to see that, but you know, in the short term, I think we're using this as a research tool to tell us better on what are the key variables to get better crystals.
Great questions. Oh, we have one more, sorry.
This question comes from a K through 12 student with the Society of Women Engineers. And how will this, in a sentence or two, in future missions, incorporate biochemical research and learnings?
One of the things I've been very fortunate in that I worked with NASA during the shuttle era, and now currently working with CASIS. And it always seems like every time we plan an experiment like this, where we plan to get single crystals, we get a lot of little ones. And we can figure out why we did that, or the opposite happens. Or we find something else out about the protein that we didn't know. And just the process of setting up these experiments, a lot of researchers improve the quality of research that they do because they're so focused in the experiment they have to do, and they're restricted in the hardware and the design of the experiment. Really forces us to do a better job or understand the processes of the experiments that we're doing.
We have one more question from social media.
Sure. This Ask NASA question is from Paul, and he asks, will those crystalline experiments be returned to Earth for analysis or all done on orbit?
Yes, they will. They are definitely coming back and in the Dragon, and we'll bring them back to New Jersey and characterize those with a battery of biochemical experiments.
Great. Thank you again, Mr. Reichert, and thank you for the wonderful questions. I want to say this with even more gratitude than normal for the two researchers who are joining us today. Just so you know, they have been up since midnight, where they had to be on site getting their experiment ready to go to the International Space Station. So please join me in welcoming Rasha Hamamia, who's Director of Integrative Systems Biology with the U.S. Army Medical Research and Materiel Command, and Melissa Cassina, who is Associate Professor of Orthopedic Surgery at Indiana University School of Medicine. They have information on research that could improve wound healing. Please join us.
Well, thank you, Tabitha, for the introduction, and thank you all for being here. As Tabitha said, we haven't slept in the last 24 hours, so if we start mumbling or speaking a different language, please bear with us. I'm from the Army Medical Command. My institute is called U.S. Army Center for Environmental Health Research. We mainly focus on studying the biology and mechanisms of diseases of military relevance. So we screen for thousands and tens of thousands of genes, DNA and proteins, metabolites in the body to understand mechanisms of diseases. We focus again on the service member, and this is one of the reasons why we're working on bone healing. Melissa and I met at one of the military health symposium where we started discussing potential collaborations because we're very good on the biomarker research. Melissa is an expert on orthopedic research. We decided to work together. We have more than one project studying bone healing. Melissa had developed a drug that she's testing now for bone healing that seems to be safer than available drugs or FDA-approved drugs. So this is how we started, and we started talking about microgravity, and Melissa will tell you more about why we're using microgravity. If you go to the first slide, please. So this is the hardware that we spent the whole night loading. Now it's on the truck on the way to the SpaceX. Hopefully everything will be as planned. As you see, well, maybe I shouldn't explain more. But again, why are we interested in this? Next slide, please. This is one of the pictures that I got from Melissa, and it's published, that shows bone fractures and bone injury. Service members and soldiers coming back from the war zone, bone injury is one of the most common injuries that the service member will sustain. This is why one of the reasons why we're trying to understand what happened in the body as the bone starts healing, looking at genes and proteins and metabolites that are differentially expressed while the bone is healing. So this will help us, once we understand the mechanism, will help us also in developing drugs for bone healing. And I think I'll turn to Melissa now. So.
Great, thank you, Rasha. So as you look at this, image of this X-ray, as I think you can imagine, it's going to be very difficult to heal, and it will not heal on its own without some sort of drug therapy. So that's what the orthopedic surgeon will do at the time of surgery, is help with a drug and to allow that to heal. Now, if you go to the next slide, we're having a model using mice, and you can see there's an injury at the middle. In the slide to the left, if you go to the middle slide, that shows that it won't heal without the drug. And now if you use a drug on the right, you see it bridges and it allows for the healing of the bone. And so I think a lot of people would say, okay, great, well, you can heal bones fine on Earth. Why do we need to go to space? And you can go ahead and show the video loop while I talk about this. But really the important thing is that first image of the human fracture of the leg, that's devastating. Those soldiers are going to be about 6 months bedridden, on crutches. It's going to be a long time where they're not bearing weight. What happens to the animals that we study here on Earth? Immediately after surgery, they walk around. Very different healing dynamics when this occurs. And a lot of our drug therapies are enhanced when you are bearing weight. And so a lot of times things that work in animals don't work in humans. And we think that this is because our model is not perfect. And so by using the International Space Station, we have a much better model where we can test the therapies and hopefully better translate what works in animals to humans. And so that's really what our focus is here. And now Rasha might sum up on how we'll also take some of this with the molecular data she'll gain.
So the value of what we call the whole genome analysis is now we can screen for tens of thousands of genes and proteins at the same time. And again, understand mechanisms of healing. And what's very important is that some of these mice will be treated with Melissa's drug and on microgravity, and this will help us understand efficacy, what's happening in the body as a response to the specific drug. We can understand how this drug is healing the bone in microgravity. And again, we have the ground control, so we can compare what's happening in microgravity to the ground control. The other thing is we don't only get the bones, we can also understand how microgravity or the space environment is affecting our organ systems. So we can also study genes and proteins and metabolites in the different organs, and this will help us understand the health effects of the space environment on our organ systems.
And if I can add just one other item. So the drugs that the orthopedics currently use in the OR a few years ago were identified as having an increased risk of developing cancer in some cases. And so that's why we think our drug may be safer than what's currently out there. And by utilizing her molecular knowledge, we can try to prove that it is safer.
I would just like to finish with just letting you know that this is a huge group effort that includes Indiana University, the DoD, the CASES, NASA, and DoD Space Test Program. In the lab this morning or late at night, we had more than 40 people in the lab just working to get everything ready. So it was a huge effort, and we're very excited about it. We're very happy to be here.
Thank you.
Thank you.
Thank you both. Again, as usual, if you have a question, raise your hand. Make sure the mic gets to you before you start speaking. And if you're following along on social media, use the hashtag #AskNASA.
So obviously, if these drugs could help people wound broken bones or fractures, that would be amazing. Could there also be connections, and I ask on behalf of my mother, Charlotte Bone, who's had advanced osteoporosis from a very young age. Could it have help? A lot of those medications don't help, especially if it's already progressed. Do you think there's an impact that it could help people who suffer from that as well?
That's a great question. And so I'm sure this audience is well aware that up in space, you lose bone. In fact, astronauts lose about 1 to 3% of their bone density in a month. Somebody with advanced osteoporosis loses closer to 1% in a year. So you can imagine how much the astronauts are losing up in space. And our therapy, while it's going to be what the orthopedic surgeons use in our therapy is delivered locally, these drugs can be delivered systemically, and there is some evidence that it could help rebuild your bone systemically. So you're right, it could have applications not only for bone healing, but also for osteoporosis. Great questions.
What are some of the blood biomarkers and genetic markers in particular? I'm sure there are many that you're looking at. I mean, I'm thinking like HSCRP and white blood cells, and but I'm sure there's more.
So in the blood, we're taking the whole blood and we're screening for all 40,000 genes, 850,000 sites of DNA. So we're screening for everything. And it's, by screening for everything, we can then identify what's significantly expressed. So we don't target a specific gene or protein. We screen for all genes or proteins in the body.
Methylation and expression patterns?
Exactly. Yes, I was told that. But yeah, what we do in DNA methylation, we have we do 850,000 DNA sites to screen for methylation. We'll do microRNA, messenger RNA, as well as metabolomic analysis and protein analysis. We'll also do the telomerase activity and telomere length. Yeah, just sure. Hi.
People with injuries would spend in physical therapy?
I think that's a great question. So our drug may not heal the bone any quicker than the current therapies. I think it's going to be safer, but certainly I think as we learn what weight bearing or what weight bearing doesn't do for the bone, that your therapy regimens may change as a result.
Other questions in the room? Great, thank you both. And
thank you.
Remarkably coherent for being up all night, I have to say. Thank you very much, and thank you for the fantastic questions. Up next, we have Dr. Anita Goel, who's Chairman and Scientific Director for NanoBioSim. She will discuss her research aimed at improving response to antibiotic-resistant bacteria. Dr. Goel?
Thank you very much. It's a pleasure to be here, and a great excitement to be launching from where the first manned mission to the moon went. We are excited to put MRSA, which is a superbug, on the International Space Station and investigate the effects of microgravity on the growth and mutation patterns of these bugs. Now, what is MRSA? MRSA stands for methicillin-resistant Staph aureus, which is a bug, a bacteria that has evolved to become resistant to the antibiotic methicillin. And what happens is that this is called a superbug because it can rapidly mutate and become resistant to the currently available antibiotics that we have. And what we want to do is, by putting this on the International Space Station, is investigate what effect does microgravity have on its growth, on the mutation patterns of the genome, and the changes in the gene expression patterns of this bacteria. And you may say, well, why? What relevance does this have? Well, first, this has a practical application. If we can use, let's say we have this hypothesis that microgravity will accelerate the mutation patterns. If we can use microgravity as an accelerator to fast forward and get a sneak preview of what these mutations will look like, then we can essentially build smarter drugs back on Earth. So that's the first practical application. And if I could have the animation you guys have that? So for the past 20 years, I've had this hypothesis that the environment affects the information that's retrieved out of the DNA. And my lab works on, at NanoBioSim works on this. We can take a single molecule of DNA, stretch it out, and investigate in real time the dynamics of a nanomachine called polymerase as it reads and writes the information in DNA. And what we do is by changing different knobs in the environment, we try to investigate what's the effect we can have on the real-time dynamics of this nanomotor. And this is part of a deeper hypothesis that the environment couples into how these nanomotors read the information stored in DNA. So how is information retrieved from the genome or the transcriptome? And here on Earth, we're trying to manipulate one knob at a time, but what microgravity allows us to do is change the fundamental environment by going from Earth's gravitational field to a near zero gravity environment and see what is the effect of just changing that gravitational environment on the dynamics or on this gene expression patterns and gene mutation patterns, which all depend on this nanomachines called polymerases. And this is just the tip of the iceberg of what that means, because first we have to get an experimental effect where we can tease out that the effect that we see is a signature of microgravity and not some artifact. So that's the first challenge. And the second is, if there is a real effect, how do we tease out that mechanism of action? What is the mechanism by which this happens? Is it because we're changing the gravitational field? Or is it because we're going outside of Earth's atmosphere and there is less filtering of various background radiation? No, we don't know the answer to that. But this opens the door to start to explore the physics of these systems. And so we're actually interested on two levels, the practical applications as well as the fundamental science applications. So I'm happy to take some questions. Yes.
Good morning. Thank you for this. What in the last 20 years of your hypothesis has led you to think that either gravity or the presence of other cosmic particles outside of our atmosphere could have an impact on the DNA sequencing?
That's a very good question. So I set out with this fundamental premise that I'm going to use an analogy. So the DNA is like a piano. So the information in the DNA sequence is only part of what makes the music of an organism. The information embedded in the environment interplays with the information embedded in the DNA sequence, and together they determine the music that the organism plays. So that's the analogy part. But what led me to this is actually I'm a physicist and a medical doctor by training, and I wanted to really understand these systems from a physics approach. And it seemed to me that living systems are fundamentally open systems. They exchange matter, energy, and information with their environment, and we have to understand the role the environment plays. And most of our mathematical machinery and physics has dealt mostly with inanimate systems and hasn't come to terms with those questions. So that's a subject of a different lecture, so I better not digress. But the issue is that what I wanted to do is, using tools from, let's say, nanotechnology and quantum optics, could we tease out an effect that by changing one knob at a time in the environment, a physical knob, in that video where we're changing things like the mechanical stress on the DNA, could we change the pattern of how genes are read or written by these little nanomotors whose job it is. Now, what microgravity enables us to do is to change this macro environment around where this bacterial genome is replicating and see the overall effect on the mutation pattern and the gene expression pattern. Now, that's in my lab, we're looking at the single molecule level, but in the space lab, we're looking at the bacterial level. What's the effect on that? And there's some profound questions there, because you would assume that the conventional thinking is all the information of a biological organism is encoded in its DNA, and the counter thesis here is that there is an interplay of information in the environment and this. And a practical example is you could have two people who have the same oncogene. One may develop cancer and one may not. What's the difference? It must be something in the environment. And I could go on that, but yes.
Please wait for the microphone to get to you. Right here, in the purple.
Oh, thank you. I have not really a question, but a statement. I've unfortunately had numerous MRSA infections that my doctor has no idea why I keep getting them. I just want to say from a personal point of view, I want to thank you, and I'm truly interested in the research that's being done. Thank you.
Oh, thank you. Thanks, Sarah.
If all of your hypotheses turned out to be true, what would the on-Earth treatment for MRSA look like?
Well, this is just the first step, but if indeed we could use the International Space Station as an accelerator, an incubator to get a sneak preview of what future mutations would look like on superbugs like MRSA, we would use that information to develop better algorithms on Earth so we could inform drug discovery and in a faster way get to smarter drugs that are more personalized and more precisely targeted to the bug at hand or to the drug resistant strain at hand. And we would have those drugs ready before those mutant strains actually emerged on Earth. That's the idea of the practical application. Yes.
Oh, okay. Sorry. So speaking of the effect of the external environment on the genome, obviously looking at something in vitro is different than in vivo. And in vivo, we're exposed to the microbiome. I know there's been a lot of interest lately in the microbiome's effect on genetic expression. And so I'm wondering, are you going to be examining that at all and how microgravity affects the microbiome of even of the astronauts on board?
That's a fascinating personal interest of mine. In fact, my research institute and company, Nanobiosym, we have developed a mobile tricorder-like device that can do real-time DNA, RNA analytics that we hope to, in a future space mission, be able to put on the space station. So instead of waiting for the samples to come back to Earth to do the analysis, you could do the analysis in real time and beam the data back to Earth. But we're as healthcare stands sort of at the cusp of a new generation, there is an opportunity to start personalizing healthcare more, and by understanding the genomics, transcriptomics, microbiomics, metabolomics, by getting real-time information about these biomarkers and how they interplay with a person's health is, I think, one of the next emerging frontiers of health on Earth. And so, yeah, I'm personally very interested in that interplay, and I think the fundamental hypothesis does connect deeply into this DNA as a piano concept.
Is there any possible impact to the MRSA samples?
Oh, there you go.
Oh, yeah, sorry. Is there any possible change that can occur in flight before it gets to the space station? Like, is there something about the environment of actually traveling from Earth into space that could also affect the behavior?
Very good question. I mean, what our team has tried to do is very carefully control by designing ground controls both before the space flight and in parallel to the space flight to try to account for all these artifacts that could be different, that could potentially lead to changes in gene expression and mutation, to try to parallelize there's a twin set of superbugs, one that grow on Earth and one that grow on the space station. So we've tried to make them as close as possible. But you're right, the bacteria that go on SpaceX that then get loaded onto the International Space Station have a traumatic experience in getting there. And so we're not simulating all of that trauma, but we are simulating the same time and temperature behavior that they're going to get exposed to, in the hopes that we're trying to tease out the effects of the growth period in microgravity. And so I would say that. But I mean, I think the first thing is to try to see, can we tease out an effect that's not due to an artifact? So your question is well taken. And the second thing is to then figure out what's the mechanism of action. And that's where the sort of theoretical physics approach comes into play. Yes.
And by sending this superbug into space to the ISS, does this pose any risk to the astronauts who are up there?
Well, it is my understanding that the team at NASA, CASES, and Bioserve, who we are working closely with, have taken great precautions to contain these superbugs. It's not the first time bacteria or superbugs have been flown into space. But I believe there are 3 levels of containment, and they're tightly packaged. And there's something called a PHAB that's sort of a portable habitat for these things. So the astronauts never come into contact with these bacteria, and they're also protected against rapid depressurization, and all kinds of ingenious engineering has gone into developing this. So it is my understanding that the astronauts would not come into contact with this and be, it's really just to try to see the effects of the microgravity on their thing. The bacteria themselves are pretty shielded from the rest of the space there.
This Ask NASA question comes from John on Twitter, and he asks, any chance the increased radiation on orbit will interfere with the goals of your experiment?
Well, I think it's a very important question to tease out if there is a signature that we see. Is that signature due to a change in the gravitational field? Is that due to a change in the background electromagnetic radiation? Or is it due to some other third-party artifact that we haven't even talked about? So I think this is not the end all be all. This is the beginning of asking a question and trying to address it with the tools we have available. But it could be very possible that, as I said, you've removed the Earth's atmosphere, so that filtration is gone, and you have more background cosmic rays, gamma rays, subatomic particles that are bombarding this and could lead to a higher mutation rate. The short answer is we don't know the right answer yet, but we can ask the question, and thanks to microgravity research, try to address it. And we're at the beginning stages of addressing that. But I think what's important is to understand that most of biology and the physical sciences have kept in their own silos. And something like this kind of space research enables us to bring, it's also why I'm passionate about nanotechnology. It does the same thing at the very small and up in the sky. It enables us to bring these traditionally different silos together in an unprecedented way to ask fundamental questions that could have profound implications in our understanding of life in living systems, and also in our fundamental understanding, I believe, also in physics, because most of physics hasn't dealt with life in living systems, mostly inanimate systems. Yes.
I think when everyone hears like MRSA in space, everyone starts to sit up and pay attention. But outside of that specific
attentive
thing,
audience,
right? But outside of that specifically, what sort of things are you hoping that you might be able to find out outside of even the superbug realm? Since we're talking about genetics here, and this is something that you're on the forefront of.
I think MRSA is a model system. The fundamental question is, what's the stability of a genome or a transcriptome, and how is that affected by the environment? Specifically, the microgravity creates an extreme environment that we wouldn't normally experience on Earth. But can we, by pushing the limits on that system, can we drive this system into a behavior pattern that reveals new phenomena, which then extends our understanding of these systems? So if you wanted to expand it in terms of biological or medical relevance, I would say that there are a number of diseases, conditions that become resistant, that evolve to become resistant to our current therapies. Bacteria infections, viral infections, cancers can become drug resistant to various chemotherapy because of an evolution that they're undergoing. So the knowledge that we could gain at a very fundamental level by understanding the role that the environment or the microenvironment plays in driving the arrow of evolution of these systems, and the understanding more about the stability of the genome, the transcriptome, the microbiome, and how they interact, would help to inform our own, our deeper understanding, but how we develop therapeutics to these, and how do we target these kinds of rapidly evolving systems. So one of the reasons why some of these bugs and superbugs are deadly, or viruses are deadly, is because they rapidly mutate. And what's causing that mutation is one question, but if we understand how they mutate and where they're going to go and mutate to, that would help us anticipate that and build better drugs ahead of schedule. Yes.
advancing the way it is and all the different areas and fields that they seem to be in right now, how often are you revisiting certain research that you may have done and taking into account what you found or what they may have found in another field and applying it to your own?
For me, that's a daily, what you want to call it, a daily passion, because somebody once said that it's not about always discovering new lands, but looking at things with fresh eyes. And I think that we always have to look at the data before us with new eyes, and as we integrate information across different silos and backgrounds, I think it gives us fresh insight. I think the International Space Station, microgravity, is an excuse for us to relook at our accepted paradigms and ways of thinking from a fresh perspective. And once we do that, we learn new things, we discover new ways of looking at old things. So it's not just about the new data, but it's about looking at the old data in new ways. And I think one should keep doing that. Any other questions?
Great.
Okay, thanks.
Thank you, Dr. Goel, and thank you for the wonderful questions. We look forward to hearing more about these investigations as the work progresses over the coming months. Thank you for the wonderful questions. We had a rather engaged audience, so thank you for that. And to our participants for their groundbreaking work. That's it for our preview of What's on Board from NASA's Kennedy Space Center in Florida. Keep following along via social media at NASA, on Twitter, on Facebook, and keep up with everything that's happening on the International Space Station at nasa.gov/station. Thank you.